summation m goes from 0 to n minus 1 x1 of n, and summation L goes from 0 to n minus 1 x2 of L, and summation k goes from 0 to n minus 1 a to the power of k, where a is equal to e to the power j2 pi n minus m minus L over n. So we have seen this expression many times before, and we very well know what is value of this geometric progression is. Summation a to the power k will be n when a is equal to 1, and it will be 1 minus a to the power n minus a when a is not equal to 1. K goes from 0 to n minus 1. Now then, let us see, for a equal to 1, n minus m minus L will be an integer multiple of n. Since if a is to be 1, then e should have the power of e to the power, please disregard the previous statement. What I mean to say is, if a is to be equal to 1, then this expression must be equal to 1. And this can be done by taking e in the form as e to the power j twice pi theta. This will always yield a value of 1, which we have shown before. And in order to do so, this term must be an integer multiple of n. So what will happen? The n and n will cancel each other out. The remaining value will become something like this, and this whole term will be becoming 1. So I hope you understand that. Now, when a is not equal to 1, then a to the power n is equal to e to the power j twice pi n minus m minus L n, just putting in the value of k over here, which is equal to n by n. So these two cancels each other out, and this becomes once again the form that I have shown over here. So this becomes equal to 1. So 1 minus a to the power n by 1 minus a will be equal to 1 minus 1 by 1 minus a, which is equal to 0. So what we get now is that summation of a to the power k, where k goes from 0 to n minus 1, is equal to n for a equal to 0, a equals to 1, and 0 for a not equal to 1. And hence e to the power j twice pi k n minus m minus L over n, when summed from k equal to 0 to n minus 1, will be equal to n for multiple of capital N That means n minus m minus l must be equal to qn, where q being any arbitrary integer, and 0 otherwise. Let us mark this as equation number 2, and we mark this line as equation number 1. So what we do now is, using the value of 2 in 1, we get x3 of n to be equal to 1 over n summation, where m goes from 0 to n minus 1, x1 of m summation of l goes from 0 to n minus 1, x2 of l, and simply plugging in the value of n over here. So in the next line, what we can do is bring this n out, and if we are to take x2 in this summation, we must change the value of l to our newly assumed value, which is summation x1 of m times x2 of n minus m minus q of n. So if we do one line over here, l we take over here, this becomes n minus m minus q of n. So just replacing the value here, m goes from 0 to n minus 1. Now this can be written as summation n gets cancelled, m which goes from 0 to n minus 1, x1 of m, x2 n minus m over, you can write q of n or n, doesn't matter, because this means this is a form of circular shift. This is another way to write it. As I have shown before, circular shift can be written as n minus n plus n minus m, or any multiple of n. This can be 1n, 2n, 3n, or even 0n. This is also true. So we can see that this is nothing but the mathematical formula of circular convolution in DFT domain. So we can very well write that x3 of n is the circular convolution of the given sequence x1 of n and x2 of n. So what we have essentially done is started with the transformed domain signal, multiplied with one another, and worked our way down to the circularly convolved time domain signal. So this is our circular convolution property, a bit heuristic, but if you refer to it very closely, it is not at all difficult, I think. Okay, now let us move on to the next property, which is the symmetry property of DFT. The symmetry property of DFT. This property states that if x of n has a DFT pair of x of k, where x of n and x of k are both complex quantities, then there will be some sort of symmetry, and we'll look into that. So x of n, since it is complex, it can be written as xr of n, which is the real coefficients, plus j xi of n. And consequently, we can do the same for x of k, which can be written as capital XR of n plus j capital Xi of, this is k. Let us mark it as equation 1 and this is equation 2. Very well. So, as per the definition of direct transform, x of k can be written as summation where n goes from 0 to capital N minus 1 x of n e to the power minus j twice by kn by n. Plugging in the value of x of n, we get summation n goes from 0 to n minus 1 xr of n plus j xi of n e to the power minus j twice by kn over n. Now this term can be further expanded using the Euler's relation. So we get x of k to be equal to summation where n goes from 0 to n minus 1 xr of n plus j xi of n. This over here becomes cosine of 2 pi nk over n plus minus j sine of 2 pi nk over n. Now we are to multiply this two expression and decompose it. So we get summation xr of n cos 2 pi nk n plus jxi n cos 2 pi nk over n jxr, this is small x of n sine 2 pi nk over n minus j squared xi n sine 2 pi nk over n, where n goes from 0 to n minus 1. So j squared is obviously equal to -1. So we can simply rewrite the expression x of k to be equal to summation xr of n cos 2 pi nk over capital N plus j xi, this is small x, I keep doing that mistake, of n is 2 pi nk over n minus j xr of n sine nk over n plus this minus and minus becomes plus xi of n 2 pi nk over n. Where n goes from 0 to n minus 1. Now if you look closely, this can also be divided into the real and complex part, I mean the imaginary part. So this part over here is a real part. This part, since j is multiplied, this is an imaginary part. Once again, this is an imaginary part. And finally, this is a real part. So what we can do now is just separate the real and imaginary part and find an expression of, over here, xr of k and jxi of k. So let us do that. So xr of k will become summation, where n goes from 0 to n minus 1, xr of n cos 2 pi nk over n plus xi of n sine 2 pi nk over n. Mark it as equation 4. And xi of k equal to, there is a negative sign, summation n goes from 0 to n minus 1, xr of sine 2 pi nk over n minus xi of n cos of 2 pi nk over n. This is equation 5. Now from the IDFT relationship, we can write x of n to be equal to 1 over n, where summation k goes from 0 to n minus 1, x of k e to the power j twice by kn over capital N, which can be further expanded, 1 over n summation k goes from 0 to n minus 1, xr of k j xi of k. So e to the power j twice by kn over n. Now, as previous, we can expand this using the Euler's relation, and multiplying these two expressions, we can get the values of small x of r of n and small xi of n, like that of xr of k and xi of k, which we have seen in this part. So similarly, xr of n will be equal to 1 over n summation k, which goes from 0 to n minus 1, xr of k cos of 2 pi nk over n minus xi of k sine 2 pi nk over n. Then xi of n can be further written as 1 over n summation k, which goes from 0 to n minus 1, xr of k sine 2 pi nk over n plus xi of k cos 2 pi nk over n. This is our equation 5 and equation, this is 6 and 7. Now, in order to look up at the symmetry, what you can do is just plug in the values of xr of n over here, or otherwise over here we can find, equating these 4 equations, we can get very different values of symmetry, for which I will ask you to refer to your book, as time will not permit us to show the symmetry in details. But all the mathematical calculations part I have shown over here. The rest is quite algebraic, and I think you can use it on your own. You can look up to the book for reference and determine the various symmetry property. So with that, we come to the end of our discussion of the properties of DFT. I haven't proved all of the properties, although I suggest that you look up the properties that I have not shown, its proof as well, the linearity, the Percival's theorem especially from the book. And with that, let us close the properties of DFT and move on to some of mathematical examples.